out. So last time we started talking about hypothesis testing, and this is sort of the last topic that we usually cover in the course. We'll see. And the idea is that we can view hypothesis testing as a form of, or in the context of decision theory, by formulating the problem. As before, we have a probabilistic model, so the background is the same basically. The only thing that this, makes it different than an estimation problem is that we only care about where the parameter lands in one of these two sets, these two disjoint subsets of the parameters. So omega naught. So we have seen sort of more formal statement. So we have the null hypothesis, which is the assumption or assumes that theta belongs to omega naught, and H1, the alternative, is the assumption that theta belongs to omega 1. So a non-random test can be specified as, we pointed out, something like this. So it's a decision rule, delta x, which in this context is called a test. And it's just, when it's non-random, you have to decide whether you're under the null or under the alternative. So the output is either 0 or 1. And so if you think a little bit about this, it's equivalent to specifying a subset of the sample space S, which we refer to as the critical region of the test. And this critical region tells you when you want to declare the alternative, when you want to declare 1. So the test would be the indicator that x belongs to S. So this is just to remind you, this is 1 if x belongs to S, 0 otherwise, which is x does not belong to S. So the critical region is where you reject the null. And there is this power function for any test. So it depends on delta. We're not showing the delta here, but it also depends on the parameter. So if you look at the probability of rejection, basically the probability that x belongs to this critical region, that's called the power of the test. And depending on where theta is in the sample space, this is going to vary. Sorry, in the parameter space. And you can see that this can be as written as the expectation of the test function, basically, or the decision rule. So what is an ideal power function? It is one which is exactly 1 when you're under the alternative, the parameter is under the alternative, and exactly 0 when you're under the null. So in practice, this can't happen unless you have a very simple, let's say, noiseless problem. So you want to approximate this. This is the ideal, like, indicator theta belonging to omega 1 is the ideal power function. So you want to try to approximate that. So because we can't achieve this, we usually work with like the best possible over each set. So the best, so you want this to be large, beta theta, you want it to be large over the omega 1, and you want it to be small over omega naught. So you look at the maximum that it can be over omega naught. We call this the significance level, or the level of the test. And the smallest that it can be, infimum, over omega 1. That's the power of the test. So these two are in conflict. So if you try to, let's say, decrease alpha, you usually have to increase, sorry, you usually have to also decrease beta. If you try to increase beta, you usually have to also increase alpha. So you want alpha to be small, beta to be large, but we can sort of have both at the same time. So the Neyman-Pearson sort of lemma, or the way that these guys looked at the problem was, okay, let's assume that we can achieve a particular, we can like tolerate a particular significance level. So let's say what I'm going to allow myself is like 5%, this being like 5% at most. And then try to see if I can maximize the power under that condition. Okay, so what is the most, this is referred to as the most powerful. What is the most powerful test given a particular significance level? So if you think about the power function, this is basically, like if you think about the frequentist interpretation of the power function, it just tells you if you repeat the experiment many times, what fraction of the time you reject. And so if I gave you like a significance level 0.05 and you manage to stay below 0.05, it means that under the null, for any theta in omega naught, no matter which one you pick, if you repeat the experiment many times, at most 5% of the time you're going to reject, which is what like classically like 5% or 1% is what people have been working with. So you can make it 0 otherwise. So you let it like be a little bit above 0 and then try to find the best possible test in the sense that it's most powerful under the alternative. Okay, is the idea clear? Questions? Comments? So this has a very classical solution attributed again to Neyman and Pearson. It's called Neyman-Pearson lemma. So in order to solve this, okay, so maybe just a detour before we try to do that. We can also look at the randomized version of a test or a randomized test, which is a randomized decision rule. This is similar to the randomized decision rules that we talked a little bit about when we discussed Rao-Blackwell. The Rao-Blackwell theorem. So instead of outputting an exact 0 or 1, you might decide to flip a coin, let's say, and decide. Alternatively, you can say, my decision will just output sort of the probability that I accept each one or reject the null. The probability that I reject the null given x, I'll call this delta x. So you can think of a randomized test as either this or a deterministic test given x and some extra source of randomness. So to implement this, you would flip, for example, you'd have a Bernoulli, like given x, you'd have a Bernoulli with probability delta x, and then your decision rule would be like delta tilde x and b would be just b, something like that. Okay, so you can think of a randomized decision rule as a deterministic decision rule, which depends on x and the extra source of randomness, or you can think of it as just giving you the conditional probability of rejecting the null given x. It doesn't, just their equivalent ways of thinking about it. So this means that the delta x is something between 0 and 1. So I allow anything between 0 and 1 because I'm interpreting it as a probability. You can go ahead and verify using the smoothing property that this formula for the power function is still valid. The power is the probability of rejection. And if you think about this, this is like the expectation of delta x given, actually not the expectation. Yeah, sort of. I believe so. Something like this, and then if I take expectation another time, then I remove the x. And this is a little bit, okay, this is not necessarily good. So let's say this is, Yeah, I mean, it's like cyclic. It's okay, but I'll let you try to figure out the notation. This is just a little bit weird because this is just going to be equal to delta x. And it is equal to delta x. But you have to interpret this as the conditional probability and then take the expectation. In any case, it's it's a simple concept. Okay. So so we let randomize this as well because it allows us to achieve certain things. So the main reason that we want this is that generally, if you're given a budget of alpha for the significance level, you want to achieve exact alpha. You don't want to be below it. And sometimes you have to randomize to be able to achieve the exact significance level. That's the only reason that we actually care about this. Okay, any questions? Okay, so let's move on. So the Neyman-Pearson criteria is like this. So let's say, think about the simplest case first, where omega naught and omega 1 just contain a single element, theta naught and theta 1. So this is sometimes called simple hypothesis testing. So then the significance level is just going to be this guy, like the supremum or the null parameter space is just, there's just one element there. So you get the expectation on the theta naught. That's the significance level at the level of the test. So I want this to be less than alpha, less than or equal to alpha. And this is just the power of the test. I don't need to take the infimum. Basically, infimum over omega 1 would just be equal to the power at theta 1. So that's the power of the test. And the Neyman-Pearson criteria tells or suggests solving this optimization problem. Maximize the power subject to an upper bound on the level. A solution of this would be called a most powerful test for significance level alpha, or at most alpha. So what Neyman-Pearson lemma tells us is that the solution is given by a likelihood ratio test. So if you think of so these, there is a, let's say, a density for each of the probability distributions that you're looking at, p theta of x. And if I look at the ratios of the densities, p theta 1 of x divided by p theta naught of x, this is a likelihood ratio. And the Neyman-Pearson suggests that we should reject if this is large. This is basically the likelihood evaluated at theta 1 divided by the likelihood evaluated at theta naught. So if this is bigger than 1, it means that the likelihood for that observation of the model with theta 1 is bigger, which is reasonable to reject in that case. So the test is basically this. So 1, if L of x is bigger than tau. And there's this extra term, which is introduced, basically achieve that level alpha, exact level alpha, plus some gamma times the indicator L of x is equal to tau. So if L of x is never equal to tau, like the probability that that happens for a given, for any x basically is 0, which happens, let's say, under continuous distributions, then we don't need this there. So it's just that part never happens. But in cases where the distributions have like masses, point masses at certain points, it could be that L of x equal to tau is not a non-trivial event. Then we have this gamma, which is between 0 and 1. So then we'll be dealing with a randomized test. So this is just equivalently, okay, so maybe I don't have it here. You can just like simplify it like this. So this is 1 if L of x is bigger than tau, gamma if L of x is equal to tau, and 0 if L of x is less than tau. So we would have gamma is generally between 0 and 1. If L of x equal to tau never happens, then we have a deterministic test, non-randomized test. And if that option has positive probability under the null, then we need that gamma, and you're dealing with a randomized test. What they're saying is that when LOX is equal to tau, we flip the coin with probability gamma and reject that probability. And for simplicity, I'm going to write P naught and P1 for P theta naught and P theta 1. So LOX will be this. So we're going to prove this result, but is the idea clear? So it's a very nice, compact solution. So it gives you the structure of a most powerful test. So the only thing that's not specified here is this tau, and not actually gamma. Anyone knows how we would like to specify these things? How do we set the threshold? Anyone on the online front? So we'll set the threshold and gamma if need be to make this level exactly equal to alpha. Okay, that's what we are going to do. We're going to use all the budget, so we're going to push it to alpha. And given this freedom with gamma here, part of the name and Pearson lemma is that we can always do that. So you can always make the test such that the probability of rejection under the null is exactly alpha. And that's part of the idea of the lemma. Okay, feel free to ask questions. Otherwise, this is an informal proof, which I think is interesting, more informative maybe than the formal proof. The idea is this is an optimization problem. I have two expectations here, but they're under different parameters. So there is a way to translate expectations under one probability distribution to another probability distribution. Anyone remembers the general idea there? Yeah. Yes, using. Great, yeah, so that's the idea. So to translate from one expectation under one measure to the other one, you do the change of measure by basically multiplying whatever you're taking the expectation by the likelihood ratio and take the expectation under the other measure. So basically, if I'm taking the expectation under parameter 1, just like theta 1, this is like this. I'm going to replace it by L times P naught. So L is P1, sorry, P1 divided by P naught. And I get the expectation of delta L under P naught. That's the sort of change of measure idea. We can worry a little bit about division by 0, but we talked about that before. You can go back to those slides. This is valid as long as P1 and P1 and P2 are mutually absolutely continuous. At least P1 has to be continuous, absolutely continuous to P naught. So if I do that, then if you think about this problem, a common approach to solving constraint optimization problem to introduce Lagrange multipliers. Right, so this is a scalar, or like a single constraint. I'm gonna introduce a parameter lambda, Lagrange multiplier lambda, and bring that constraint into the object. So lambda times, you write it as expectation of theta naught, delta minus alpha less than 0, and then the Lagrange multiplier times this added to the objective is how you proceed. And then you maximize this over delta without any constraint on delta. And the idea is that there is some lambda for which the solution of this problem is the same as the solution of the constraint problem. So if you believe this, this is the hand-wavy part. You have to formalize that this is the case. But if you agree with this, you can at least like get the insights about what happens. So I want to minimize this. So the lambda alpha doesn't matter because it doesn't depend on delta. so that we can discard. So we're looking at the argmax. So the argmax sort of simplifies to this. So I can discard this term, and the argmax simplifies to this expression. And then I'm going to use the change of measure to replace this guy with expectation, or actually the other one, expectation under 0 or theta naught delta times L. Okay, and then I can combine the two expectations. I get this expression. Factor out delta. So I'm trying to minimize this. This is basically the compact way of writing expectation under theta naught delta x times L of x minus lambda. And I have to specify basically this delta, which is at every point x, or almost every point x. So my variable is this function delta x. So if you think a little bit about this, you sort of realize that the solution depends on the sign of this. So for any x, if this is positive, the maximum that delta x can be is 1. So I want to maximize. So it's like the sign. It's like you're maximizing a linear function. It depends on the sign. So if the sign is positive, I want this to be as big as possible. So I'm setting it to 1. If this is negative, I want it to be as small as possible. I set it equal to 0. When this is equal to lambda, it doesn't matter what you do here, right? So it could be anything. And that would be the solution. The solution, I mean, there is some lambda for which the solution looks like that. And that's the end of the story. So this is the likelihood ratio test. Okay. So you write it that this way, you'd see immediately what the solution has to be. It's basically pointwise. If I achieve the pointwise optimality, then the expectation has to be as well. Okay, is this solution sort of okay? Okay, there is also a formal proof, if you don't like this. This is the formal statement. So we have rewritten the likelihood ratio test in this fashion by multiplying out by p naught of x. This form has a bit of a advantage because everything could be 0 and everything is well defined. You don't get 0 divided by 0. So for a formal proof or for a formal statement, this is the preferred version, but it's just basically the likelihood ratio test. You can see if you divide both sides of these conditions by p naught of x, you get the same sort of expression as before. So this is a test parameterized by t. T is the threshold, that thing that's there. And then gamma is that randomization, or the probability of rejection when that corner case happens. So Neyman-Pearson lemma tells you that for every alpha in 0 to 1, there are t and gamma such that I can achieve the exact significance level alpha. Basically, the expectation under the null of this test, which is the probability of rejection under the null, is alpha. That's how we set the tau and t or gamma, t and gamma. And if a likelihood ratio test satisfies this condition, then it's the most powerful test at level alpha. And furthermore, any most powerful test at level alpha can be written as a likelihood ratio test. So there's nothing else out there, sort of. Okay, so to prove A, we're going to do a proof by picture, basically. So what you would like to do is, let's see. So let's define this quantity, GT, which is just the, let's say, the complement of the CDF of L of x under the null. Okay, and you can think of it as basically the probability that T1x is bigger than T naught of x to avoid division by 0. But it's just basically the CDF of the likelihood ratio flipped. So if you look at the plot of this, what do you think it would look like as a function of t? Generally, some of the properties of it. Okay, so like where we should start and where we should end is like, yeah, it's like close to 1, or like it can be above 1. So let's say generally you would have like asymptotically approaching 1. It's like the flipped CDF, and then it goes down monotonically. So if it goes down like this continuously, then what we can do is that if you give me a threshold alpha, it's gonna be monotonically decreasing. It's gonna hit this at a particular point, right? So that would be like theta t star. So if z t star is alpha, I can find that. Basically, it's just going to be the quanta. So the quantile function, the inverse, it will be inverted would apply to alpha. And you can easily see that if I set gamma, like in this case, I'm going to set gamma equal to 0. And basically, this guy, fz t star is just the probability that this is rejected. Okay, this is 0. The probability of rejection is just the probability of this, which is just fz of t star, which is equal to alpha. So we achieve what we want. Simple. There is no randomization. The case which is a little bit more interesting is when there is a probability or like a lumped mass of probability at a certain point. So let's say there is this point. At this point, the likelihood ratio takes some value, let's say t naught, or let's say, yeah, t star, let's say, with probability, some probability. So what would happen is you have to think a little bit about whether it's like right continuous, or is the CDF right continuous or left continuous? Okay, if it's right continuous, then this is also going to be right continuous. Just double check it. Okay, but something like this happens. So if the discontinuity happens at this point, and let's say alpha is here, we'll still find, so we'll still have a unique solution here. There's no need to randomize. But if there's this discontinuity, and let's say alpha passes through this point, like the empty space here, right? Then I can't find a point such that fz of t is alpha, right? I'm gonna either be very close to the point which is like hollowed, or this like solid point. So there's no way I can achieve that exactly. So that's where the randomization comes in. By randomization, I can get any points between these two, basically. So what you're going to do in that case, you're going to set t star to be exactly this t star, the point of discontinuity. And then how do we set the gamma? So if you want to set the gamma, you have to think a little bit about what this is saying. So the probability of, so the expectation under the null, I want this to be alpha, delta t and gamma x, I want this to be alpha. So this is going to be 1, just like probably, this is the probability, right? 1 times the probability of, let's say, L of x being bigger than t, plus gamma times the probability of L of x being equal to t. You can just justify this by thinking this is exactly what the meaning of the expectation is. And I know that, let's say, at t star, this guy is going to have a certain value. So let's call this fz of t star. I know that this is strictly less than alpha. And so what I'm going to get is I'm going to solve this for gamma. So you get alpha minus fz of t star divided by probability of Lx equal t star. We could just call it this. So that would give me gamma. Call it gamma star. Okay, and this is easily seen to be, this has to be bigger than 0 or bigger than or equal to 0. If it's equal to 0, we're back to the previous case. And it has to be also less than or equal to 1. It's not hard to see it's less than or equal to 1 because both alpha and f are between 0 and 1. So actually, no, it's because we're dividing by something. So is it less than or equal to 1? So it's easy to see from this point because it's just the difference. It's this difference, right, divided by this. So it's just a fraction of that, right? So I'm dividing this part by this whole thing. So this is basically the size of the jump. It's not obvious that's between 0 and 1, but looking at the picture, it should be between 0 and 1. Okay. The size of the jump is the probability that you're exactly equal to that. And alpha minus that is just that fraction, which is the distance between the value at t star and alpha. So it's valid, so it's a valid probability, and we're done, sort of. So you can justify this for yourself. The other case that could happen is that you get a flat piece of this complementary CDF, in which case there are many solutions. So like case 1 or case B, there's also a case C, where you like have something like this and then a flat piece. So when does that happen? Like flat piece of a CDF or complementary CDF. Okay, yeah. So there's no chance that the random variable lands there. So it's either like in this interval or in this interval, but there's no probability of landing here. So it gives us this flat piece, and if it happens that the alpha is such that you hit exactly this flat piece, then what should we do? Do we need to randomize? Interesting. T smallest, you mean this one. So any t in this region would satisfy the significance condition. Yeah. So the thing, okay, the issue is yeah. So the it's interesting. So it's a this is the CDF of L of x under the null. So the question is, so under the null, it doesn't matter. Well, what about the alternative? So this Neyman Pearson tells you it's going to be a most powerful test as long as you satisfy this. And you can satisfy this with any threshold in that like range. Because you can see it's just that probability turns out to be. So gamma would be 0, and that probability is that true? Or yeah, if I set this equal to 0, I can set this equal to alpha for various t's that are in this range. So does that affect our power? Should intuitively, if there's no probability of landing in this interval, even under the alternative, then you're fine. But is that the case? Is that going to happen? Under the alternative, Okay, yeah, so there is this probably assumption. Yeah. Are we assuming that? Actually, we're not assuming, I think. They're absolutely continuous with respect to something, but there's no need that P1 of x is absolutely continuous with respect to P naught of x. If you write things like that, I'll make you think about this. So Neyman Pearson tells that any of these tests are most powerful. But the question is, can I get a better power? Because this is telling you what happens under the null, but there is a bit of P1 of x there. So it's like the probability that P1x is bigger than this. So roughly speaking, this is 0, okay, over that range. Or is it 0 really? Probably 0. But think about this. Any one of those values work for alpha, sorry, for achieving the significance level, but the question is that do all of them have the same power? Or you're missing something in the Pearson letter. How should we use it?
The expectation of that like under the null is of x is equal to alpha.
Yeah.
That then the expectation of times the, or I guess that's not all the time.
Yeah, the problem is this, we can define yeah, you can say something like that P1 divided by P0 divided by P1. This is the same as this. Okay, let's think about this offline. Let me know once you discover what is going on. It's an interesting case, but you don't need randomization. The point is that you don't need randomization in this case. The question is that whether you're gonna change the power if you change the threshold. Maybe you can also look at the proof. This is the formal proof for the most powerful part. So in order to do the proof without the Lagrange multiplier, so worrying about the validity of the Lagrange multiplier approach, what we are doing is, so the claim is that the likelihood ratio, so that delta star be the likelihood ratio test of significance level alpha. There could be multiple of these things. And apparently the proof tells you that any of them would work. So let delta be any other rule satisfying the constraints that we have. So this is the constraint. Okay, delta is some arbitrary rule that satisfies the constraints. Delta star is the one that achieves alpha, and it's a likelihood ratio test. Okay, so we already know that the significance level of delta should be less than or equal to that of delta star. Then you look at this guy, you write this inequality, and you look at it and see that this holds always. So anyone can justify why this inequality is true. So delta star is basically, remember, delta star of x is 1 if P1 of x is bigger than or equal to P0 of x, or you can write it like this. If this quantity basically, if this is bigger than 0, it's gamma if this is equal to 0, 0 if this is less than 0. It's the same quantity. It's called a star. Star is bigger than 0. Star is equal to 0. Star is less than 0. It's the same thing here. So you have to consider these three cases. So if a star is bigger than 0, strictly bigger than 0, I can just cancel it from both sides, right? So this says delta star. Actually, do we need to cancel it? Yeah, so cancel it from both sides. And I know that when this is positive, this is 1, right? So delta star is 1, and delta x has to be less than or equal to 1, so it's true. If the star is 0, then both sides are 0. If it's less than 1, sorry, strictly less than 0, then I can cancel it and flip the sign of the inequality, and delta star in that case is 0. So this is that delta x is bigger than or equal to 0. So consider three cases. In all the three cases, it just trivially holds. And because of the way we define the delta star. So this equation is true for all x. I can plug in the random x and then take the expectation under the null of both sides. The expectation is linear, right? So it passes through, and like the expectation of this part is going to be the expectation under the actually the integral, not the expectation. So multiply both sides by the integrate with respect to dx. Okay, integrate with respect to the underlying measure. This would give you the expectation under the 1. This is the expectation under the null. Similarly here. Okay, and then I rearrange. So if you rearrange, you get the next inequality. So you move all the expectations under 1 to the one side. So this one and this one goes go there, and then this other guy under the null, these go here. And you can just do the algebra. And this is less than or equal to 0 by assumption. Okay, this is the constraint that we have. So this proves that the other side is non-negative or non-positive, and so just means that the power of delta star is bigger than or equal to the power of delta. So this very simple argument just proves that any likelihood ratio test with like anything that looks like this, and so to satisfy the significance level would be most powerful. And in the previous case that we had, like the case, this case, it should be that they're all just to have the same power, because you can take one as delta star, take the other as delta, and then rearrange. Like flip the order, you get both sides of the inequality, and so you should have the same power. But it would be nice to be able to like argue what exactly happens. But this is the proof, okay? Very simple and very general. I don't think there is an assumption that P1 and P2 have to be absolutely continuous with respect to each other. They're just absolutely continuous to some underlying measure, so that we have these densities. Okay. So this is a very interesting result, and like the foundational result in like hypothesis testing, like theory of hypothesis testing, let's say, like optimality. This tells you something about optimal tests. The optimal tests look like likelihood ratio tests. So you can do better. And any questions about Neyman-Pearson lemma, the proof? I'm not proving the last part. You're welcome to consult with the Keener or some other book. We're going to focus on likelihood ratio tests. So let's see maybe an example. So if you have normal with mean theta variance 1, and you have two hypotheses. Simple hypothesis, theta is equal to theta naught, and theta is equal to theta 1. This is the like a simplest, perhaps, hypothesis that you can think of. You just have a single draw from a normal distribution, and you don't know the mean. You just know that, let's say, it could take these two values. So the idea is to form the likelihood ratio. The constants will cancel out. So that's the likelihood ratio after cancellation of the 1 over root 2 pi. And then you usually take the log. So the idea is that the likelihood ratio, so this is a case where everything is continuous. So this is a, x is a continuous variable under the null, and L of x is going to have, it's always positive, and the distribution is going to be continuous, so there's no need to randomize. So the likelihood ratio test is going to reject if L of x is bigger than t for some t. Okay, you don't have to worry about this being equal to t. So you have to just determine the threshold. What you do is that you take the, for example, log of both sides of this. So when I take the log of this, I get this expression and I get log t here. And then I do some manipulation, some algebraic manipulation, I get this expression, hopefully. At this point, I want to simplify further. This is like formal version. So I want to divide basically by this. But if I divide by this, the inequality is going to change direction if the sign is negative. Okay, what I'm trying to do formally is divide by the absolute value, which is always positive. So if I divide by the absolute value, basically I get the sign here. So divide by, or you can consider two cases. Divide by this, theta 1 minus theta naught, divide by the absolute value is just the sign of theta 1 minus theta naught. And then the rest I move to the other side, okay? And now I can, because this wasn't like not determined yet, I can call this a new threshold, okay? At this point, I just want to, let's say, figure out the structure of the test. When do we want to reject? And whatever this is going to be another threshold. So this is what you often do when you solve these types of problems. You don't necessarily have to worry about the original threshold. You simplify things and you figure out the test rejects if x times the sign of this is bigger than tau. Now I'm going to figure out the tau. I don't have to worry about the original threshold. So let's say theta 1 is bigger than theta naught. The test is just simply x bigger than tau. So a likelihood ratio test rejects if the observation is bigger than the threshold, which is very intuitive. Okay? So if I have two normal distributions, one theta 1 here, the mean is here. The other one is as the mean like theta 2. And I observe like a single observation to decide which one it comes from. I'm going to reject the null, which is this, if x is large rather than not. Just have to figure out how large it should be. So the test is just delta x is indicator x bigger than tau. And in order to set tau, I just have to require the significance level constraint. So under the null, the probability that this is equal to alpha gives me an equation that I can solve for tau. Okay. So this is basically the expectation under the null of delta x being equal to alpha. And it's rather simple to see. So let's say x is under the null is like theta naught plus z, where z is standard normal. So the probability under the null that x is bigger than tau is equal to the probability that theta naught plus z is bigger than tau. The probability that z is bigger than tau minus theta naught. And this I'm calling q. Q function is like the complementary CDF for a standard normal. Tau minus theta naught. So if I set this equal to alpha, I can apply the inverse of the q function. I get q inverse alpha plus theta naught. So that's the threshold that I get. Okay, and the q function is like well known in engineering. It's related to the quantile function. It's just the complementary version of it. Okay, so then you're done. So that's the test. I can also compute the, so is this clear? So how we did this? So this procedure is very helpful. In general, you don't want to necessarily stick with the threshold on the original likelihood ratio. You just manipulate it a little bit and things simplify. So maybe before we move on, what happens if theta naught is less than, or theta, wait, sorry, this is theta naught. So this is theta 1, this is theta naught. So what if we have the other direction? So theta, we assume theta 1 is bigger than theta naught. What if theta 1 is less than theta naught? It's just the flip, yeah. So when you divide by, so this is going to be negative. When you divide by it, you get x less than negative tau, which is now a new threshold. So you're going to reject when x is small. And then you set the threshold. So you can see the likelihood ratio test picks up the right direction automatically. You don't have to worry about it. What if theta 1 is equal to theta naught? Yeah, it's just there's no problem there because you're testing whether like theta is equal to theta naught or theta is equal to theta naught. There's no hypothesis testing there anymore. So this just completely answers this question. Questions? Oh, there is something in the chat. Q, okay, so Q is this Q function. I actually have it here. Minimize the chat. Yeah. So Q is here. So it's like 1 minus the CDF. Okay. The CDF of standard normal. It's just exactly the probability that Z is bigger than X, where Z is standard normal. Okay. So then we can also compute the power. The power will be the probability of exactly the same event under the alternative. And under the alternative, so you can like subtract theta 1 from both sides here. And this is going to be standard normal under the alternative, right? Under the alternative, X is still like theta 1 minus, sorry, the normal theta 1 and 1. And so this standard normal, so this is basically Q of tau minus theta 1. And if I plug back the threshold, actually, you can see what happens. So if this is the tau that I have. This guy is tau. If I plug it in here and define this delta to be theta 1 minus theta naught, that's basically the signal. It's a bad notation because delta is used for decision rules. At this point, it's just a number here. There's hopefully no confusion with the decision rules. This is the difference between theta 1 and theta naught. And then you can see that beta is like this. Okay. Beta is just Q minus this delta plus Q inverse of alpha. This delta is like a data in the problem. So it's just, you specify how far the two, these two guys are. I mean, in general, if there was a variance here, you also had this divided by the variance. It's like signal to noise ratio. The standard deviation of the noise is 1. And theta 1 minus theta naught is the signal to noise, to 1. So this is a signal to noise ratio. SNR, basically, a measure of. So you can imagine if delta is small, the problem is harder. If delta is big, the problem is easier. And you can plot this, alpha versus beta. Okay, that's the or beta versus alpha. This is called the ROC curve, receiver operating characteristic. It's a term from engineering, from radar. You can think of this as the radar that's trying to detect an aircraft. And this is how well it does. So as a function of like beta as a function of alpha, you plot it. This is the equation basically, right? You get something like this for a like value of delta that I forgot. But that's the ROC for this. This line is the performance of like a coin flip. So if I just flip a coin, basically point flip would be a randomized rule, which is like equal to 1/2. Right? And okay, not exactly that. So what are we getting? Like what is the test that gives you this line? Can be 1/2. 1/2 would have the same, like it would be this point. So the coin flip would be this point. So this is the test that basically it's just equal alpha. Okay, x. No, that's not going to work as well. Yeah, it's actually working. So expectation of this guy under alpha is alpha, right? And expectation under the null is also alpha. So your beta is equal to alpha. That's that line. So this is like this respects. So you flip a coin with probability alpha, and you reject the probability alpha basically. So you're gonna respect your. So you can't have like 1/2 because if I flip a coin like fair coin, I'm gonna have like 50% chance of rejection under the null as well. I don't want that. I want to respect my significance level. So a random test, just completely random, but satisfying the level alpha is to flip a coin with probability alpha and reject with probability alpha. In which case the power is also going to be alpha because it doesn't matter under what you are. And so the power is going to be equal to alpha. So that's the naive sort of thing to do. Okay, and this is doing much better. So this is saying at a given like alpha equal 0.2, I can achieve a power of 0.2 trivially by just flipping the coin, but I can do much better here. And what Neiman Pearson tells you is that this part is not achievable. So no test can sort of live here. Why it tells you that? Great, yeah, non-achievable. Yeah, achievable, something like this. Because for every alpha, what the likelihood ratio is telling you is, or the Neiman Pearson lemma is telling you is that the maximum power is this basically. That's the power of the likelihood ratio test. So anything from 0 to this point is achievable. Anything above it is not achievable. So this is like some optimality. And so you come up with another test. It's like at best would be like something like that, or something like this, or something like this, but never sort of touches. So at each point, this has to be like could be like this, but it cannot go above it, which is a very interesting result. Does that make sense? And you can also very easily see that the trade-off. So if I let alpha go to 0, I'm going to have to pay a 0, like have a 0 power. But if you let it sort of slide a little bit, just sharply goes up. So a little bit of alpha allows me to have a big power. And then as like when you increase it, like there's like diminishing return. So you don't have to go. You can achieve like power close to 1, but alpha has to be very close to 1. There's like a sweet spot. It's like right around here or somewhere, where you don't need to go further. It's not like it's probably not worth it. But I don't know. It's just subjective. But you can see like the shape is concave, so there's diminishing return. Questions? So these ROC curves are very useful for comparing the performance of tests, making the simple hypothesis test. That's basically the ideal. You don't have to worry about the threshold or the alpha. You can just plot it for all alpha and then compare. I mean, again, think like different things could happen. It's like a risk function. So one could have something like that. The other one might be like that. So in some reason, like they could like not dominating each other. But there's this one which dominates everything. So there's that. But these are very useful for comparing performances simple hypothesis test. So this is the naive test, randomized. Test that gives you the dashed line. Okay. Questions? Okay, we have this. So now let's move on to what happens in the general case, which is referred to as composite or composite. Composite hypothesis testing, theta equal omega naught, theta equal, in omega naught, theta in omega 1, and they are disjoint. A typical example is, for example, I have a fair coin. I want to test whether, no, I don't know actually the fair, it's fair. So I have a coin, I want to test whether it's fair or not. That's like testing the probability being equal to 1/2 or not. Okay, this is more common. Basically, the alternative is vague, anything other than the null. And so if you want to extend the idea of most powerful tests, for this setting, it would be something like definition 1. So a test of level or size, another name for level is size. The test of size alpha is uniformly most powerful at level alpha if for every other test phi of level at most alpha and every theta in omega 1, the power of delta is bigger than or equal to the power of phi. The uniformity here is that this expression holds for all theta. Okay. So if omega 1 just contained a single parameter, this would be similar to the most powerful idea, sort of. But we want it to hold for every theta. And you can imagine, so the level also here is like the supremum over omega naught. So there are two extensions here. A test of level alpha has to have like, this power function has to be at most alpha over the null set. So we're looking at these tests. A uniform most powerful or UMP test of level alpha, it has to have level alpha or size alpha, but I also have to have like pointwise domination of the power function over the alternative parameter space. And you can imagine this is similar to the idea of uniformly most, like uniform minimum variance or something like that. You want the power to uniformly dominate. That's more closer to the idea of comparing risks. And this is hard to achieve. So this uniformity is not necessarily possible. So UMP tests do not always exist. They often don't, in fact. So, but in some cases they exist. So let's see in what cases they do exist. So let's consider, is that sort of statement sort of clear? If I give you an example, it becomes actually more clear in an example. So suppose we have a binomial observation, n and theta. This is like the coin flipping example reduced by sufficiency. So I want to test whether theta is equal to 1/2 versus theta not equal to 1/2. So what I can do is I can consider an alternative, let's say unspecified alternative, just any theta 1. Simple alternative, but theta 1 I won't specify at this point. Then I can write down the likelihood ratio. I know that the likelihood ratio is going to be most powerful for this simple hypothesis testing problem. If you write down the likelihood that this is the PMF, if you remember, just there's some sort of nx here which cancels out. Okay, this is the binomial likelihood basically. Evaluated at theta 1 and evaluated at 1/2. And then if you simplify a little bit, you get this expression. Okay, and then I proceed again as before. So I want to compare this with a threshold. It's easier to take the log of both sides. I'm going to take the log, and you can see if I take the log, it would be log, let's say t of x, bigger than, let's say, log t. This gives me x log theta 1 minus theta 1 plus n log 1 minus theta 1 divided by 1/2 bigger than log t. Okay, and then I move this to the other side. I end up getting something like x log theta 1 minus theta 1 bigger than, let's say, tau, which is log t minus n log 1 minus theta 1 over 1/2. I don't care about this particular form. It's just some constant. So you can see again that the direction of the test changes depending on the sign of this. And if hopefully what I wrote here is correct, the sign depends on whether theta 1 is bigger than 1/2 or less than 1/2, as you can imagine. If theta is less than 1/2, this is going to be negative. So when I divide by this, I'm going to flip the sign of the inequality. And so I'm going to reject when x is less than tau. S less than negative tau, which I'm calling it tau again. And then if theta is bigger than 1/2, this is going to be positive. I'm going to reject when it's bigger than tau. So tau is not the same in quantity, but just some threshold. Again, this is reasonable, right? So if I'm testing 1/2, when theta 1 is bigger than 1/2, I want to reject when things are big. When theta is less than 1/2, I want to reject when things are small. But this sort of tells you that no UMP test can exist for testing the alternative, which is, let's say, H1 is theta not equal 1/2. So let's see if anyone can see why that is the case. If my alternative is theta not equal 1/2, then what I'm claiming is this calculation or this little derivation tells us that there is no UMP test for this alternative. Anyone can maybe justify it quickly? Yeah. Yeah.
So you could compare a different data, like of the ratio test example,
Yeah.
and that's going to be like more powerful than any other test like at that value of data.
Yeah.
That's true in both settings. So it's possible to have a test that is more powerful
Everywhere. Yes, that's basically it. Yeah. So you can see that the most powerful test when theta is less than 1/2 rejects when things are small. So if I stick with this, I'm going to be most powerful for alternatives that are below 1/2. But then there's something else that's more powerful when things are above it. So this guy is going to beat my test when theta is bigger than 1/2. If I stick with this, I'm going to be most powerful above 1/2, but then this guy is going to beat me. So I have to go with either one of them. And I don't have to look at any other thing because this is going to be most powerful, at least in some part of the space. So if you think a little bit about it, there is no way that I can have something that's most powerful everywhere. So if I have something, and you know that something that's most powerful by the Neyman-Pearson lemma has to be a likelihood ratio test. So if it's most powerful over all the thetas that are less than 1/2, this has to be this test. And then it can't be the other one. So this one is beating it. If it's most powerful above by Neyman Pearson, it has to be this test. And then like this guy is going to beat it below theta. So there's no way that I can have a single uniformly more powerful test. However, the same argument shows that so no UMP for this two-sided test for this guy, but we have a UMP test for, let's say, a one-sided alternative. If my alternative is something like that, because you can see that this threshold is not going to depend on theta 1. When I'm going to set this threshold, I'm just going to use the null distribution. So I'm going to go under the null, the probability under the null, this is equal to alpha. And so that sets the threshold, doesn't have anything to do with the theta 1. And so I have a test which is perfectly defined based on the null, and it's most powerful for any theta 1, bigger than, but this is less than 1/2. So we have a UMP test for this alternative, and or like if the alternative is like the other way. One of them is UMP for this, the other one is for the other one. Again, it's UMP because I can set the test for a particular theta 1, but you can see that the test doesn't depend on theta 1 because the threshold is determined by the significance level. That's how you generally drive the UMP test. Okay, so we can stop here, come back. This idea can be like put into a theorem. When this happens, there's this property called monotone likelihood ratio. So this family has likelihood ratios monotone in this X. And this is a general property of an exponential family. And when you have it, then you have these UMP one-sided tests. But two-sided UMPs are much more difficult to achieve. Okay, I'm going to stop here, come back next time and continue. Okay, see you guys next time.